Good morning. This is segment 1 of section 4.4, the last section in chapter 4. As we've already looked at, we've investigated the graph of both sine, cosine, tangent, cotangent, as long as both transformation, as well as looked at both transformations and translations. So the last thing that really is left to do is to look at the two functions, secant and cosecant. Now, there's something that I want to, rather than go through what we've done previously, where we just simply plot a bunch of points, what I'm going to do is I'm going to use a more graphical technique to develop the graphs of secant and cosecant. So let me kick over here to the document camera real quickly. And I want to start a little kind of discussion that involves the relationship between, for example, cosine and secant. So this is section page 1. I think I'm going to use a different pen. This one's about dead. Okay, so let's consider for a second the graph of cosine. And there's a reason why I'm using cosine. It's because secant is the reciprocal of cosine. So let me just kind of try to do, I'm going to make the graph a little bit bigger in the vertical axis. And I'm going to make it, let's do it over 2 periods. So I don't need a whole lot of detail, just enough to kind of show what's going on. So this will be -1 and 1. Remember that that cosine starts at a maximum at the origin. So this graph will be y equals cosine of x. And about halfway through, so at pi, it achieves a minimum back to a maximum at 2 pi, and then I think I got that a little off base there. At 3 pi, it's back to a minimum and then back to a maximum. So this kind of oscillates back and forth through here, as you probably remember. So let's kind of fill this in, but let's use a little bit of dash, because we're not really interested in the graph of cosine. We've already looked at that. I'm going to be more interested in the graph of secant. So there's we're going to start here at a high point. We cross the x-axis about halfway between pi, well, at exactly halfway between 0 and pi. We achieve a minimum at pi, back up through the x-axis to a maximum, and then repeat the process one more time. And this isn't a real great graph, but I think we've seen this enough to kind of know what's going on. Okay, so let's consider that since secant is the reciprocal of cosine, right? And we had this discussion when we were talking about tangent and cotangent. Since secant is the reciprocal of cosine, anywhere that you have cosine equal to 0, right, which occurs here, 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 and a lot of other places as well, anywhere where that happens, you have a vertical asymptote. So if we're going to draw secant, we would start by putting in these vertical asymptotes anywhere where cosine is 0. So let me just place one here, place one here, place another one here, and finally one here. I haven't got it real well spaced out, but those should be even distances between them. Okay, so now also consider that since secant doesn't have a range that ever is any closer to the x-axis than 1 or -1, right? Cosecant never falls inside of this area, right? Ever. So we don't need a whole lot of points to figure out what's going on, because as it approaches these vertical asymptotes, it can't go, well, if we have an area where where secant is up here, it can't go down because it never crosses the x-axis. In fact, it's always going to be positive in this region. And similarly, it's always going to be negative in this region. So really all we have to do is figure out just a couple points and then it's done. So consider this, at the maximum, where cosine's at a maximum, this is actually where secant is at a minimum. And so this is a point of commonality between them. The same could be said down here of this minimum, that this is a point of commonality. The points that I'm marking are actually points that are both on the cosine graph and on the secant graph. And so I'll just kind of fill them all in here. Now, what happens as cosine starts to decrease in here? Well, the reciprocal function has to increase, right? As one goes up, the other one has to go down. They keep the same sign, SIGN, but their increasing, decreasing behavior is opposite. So really, this kind of gives us a clue as to what's supposed to happen here. Is that as this approaches this first vertical asymptote, it must go up, and then as it gets arbitrarily close, it just rockets off to infinity. The same thing happens down here when cosine is negative. Note that this is a point of commonality. As we move to the left, decreasing x towards this vertical asymptote, the graph really has nothing to do except go downward. Similarly, this happens on the other side. So we end up with these kind of U shapes, right? Let me just kind of fill this in over here. And there's really nothing to add. I mean, we could find intermediate points. Like we know that, at certain places, secant is -2 or 2, but what kind of real improvement is this going to be on our graph if we have some more specific points? Everything that we need is sitting right here. So one thing that I want to point out is that unlike, with tangent, we had vertical asymptotes, right? And we said that the distance between successive vertical asymptotes is the period. Well, unfortunately, with secant, that's not the case, right? It actually is 2 vertical asymptotes for a period. Note, here we have sort of the beginning of the cycle, and here's a repetition of that cycle at 2 pi. So the period, just by looking at the graph, the period of secant happens to be 2 pi, as it should be, because the period of the reciprocal function, cosine, is actually 2 pi as well. You can't have, some kind of a mismatch there. So just from inspection, a couple things that I want to point out. If you were to, the critical features really have to do with translation, vertical and horizontal stretching. Well, if you have horizontal stretching or shrinking, then the spacing between these asymptotes will increase or decrease. That's really the key, the clue that's happening. If you have vertical stretching or shrinking, the vertical distance between these two maximum and minimum will increase or decrease, right? And if you have some sort of translation, either vertically or horizontally, this point or this sort of feature point is the one that's critical to figuring out what the parameters of that graph are. So it's much like with cosine, it is the origin where the secant is actually at a positive minimum, because it's not really a global minimum. It's a local minimum, but it's very similar to finding the translation components for cosine. So let's try to work through this a little bit. Obviously, the A, B, C, and D terms are not particularly, they don't have any specific names, because I will be completely honest with you, secant and cosecant are not typically used or graphed for much of anything. It turns out that there is a close relationship between not necessarily the graph of secant, but actually the graph of the inverse secant that turns out to be important in a calculus context. So, I mean, there is some value in doing this just for completeness of the trig functions, but there's not a whole lot of practical value of knowing how to graph secant, because again, just like with tangent, there's not too many behaviors of physical parameters that go to infinity. In fact, I'd say there's none. So anytime you have a function that has these sort of vertical asymptotes, it's going to limit its practicality because we know that physical quantities never go to infinity or negative infinity. So now I just want to point out that I used this cosine graph as a tool. The graph of secant does not involve the cosine. So if we were to sort of clean this up and just have the graph of secant, I'm going to kind of do it a little bit smaller so I don't take up too much space here. But here's our x-axis and our y-axis, and we'll go ahead and put in the vertical asymptotes. The first one occurs at pi over 2. The next one occurs at 3 pi over 2. And then finally, we have one out here at 5 pi over 2. Now, the key to graphing these is to figure out where that local origin is, and then use the a value to figure out how far to move above or below this baseline. So we'll call this 1, -1. We've got sort of this behavior here between pi and 3 pi, or 3 pi over 2 and 3 pi over 2. We have that sort of behavior. Voila. And this should be smooth. It's not a peak down there. It's kind of like with the x squared function. It's smooth down there and actually achieves sort of a low point that certainly is not peaked. So this is the graph y equals secant of x. Okay, so what I think I'd like to do is rather than practice a graph of secant, I want to go ahead and do cosecant as well. So we're going to do the same sort of trick that we did before, where you say, okay, well, cosecant of x is equal to secant of pi over 2 minus x, and this is a cofunction identity, and we're gonna factor out a -1 just like we did previously with the other functions. So we've got secant of -1 times x minus pi over 2. And now we have a negative something. And remember, secant is an odd function, or is an even function. You can actually see this from the graph. It has the same sort of parity that that cosine has. Cosine's an even function, so secant's an even function as well. It has a mirror. It could be reflected across the y-axis and still have the same look. So as a result, this negative sign simply goes away, and we're left with secant of x minus pi over 2. So what does this tell us? It tells us that the graph of secant, or the graph of cosecant, is just simply the graph of secant, but shifted to the right by pi over 2. So without a whole lot of extra effort, we could just simply take this graph and put the y-axis here, a unit pi over 2, which means the cosecant starts with a vertical asymptote, which we already kind of knew. So if I'm just going to squeeze this in here, it doesn't need to be super accurate because, again, there's not a whole lot of detail here. But note, there's a vertical asymptote. The first vertical asymptote is actually coincident with the y-axis. And then there's another one at pi, and finally one at pi over 2, or sorry, 2 pi. And I didn't actually put these in here before. Okay, so what's going to happen here is that, there's the vertical asymptote at the y-axis. Cosecant is positive in quadrant 1 and 2. It has this minimum at 1. And in quadrant 3 and 4, it's negative, and it kind of has this maximum at 3 pi over 2. So this is the basic graph of cosecant just from using the secant function. So, I mean, that's not necessarily, that's very quick and dirty. What I'd like to do is I'd like to take a couple of equations and produce some graphs, and then take some graphs and produce some equations, which is really the harder aspect of this. So let me move on to page 2 here, and let's take an arbitrary I don't know, secant or cosecant really doesn't make any difference. So let's graph the function. I don't know, let's say y equal to 2 secant of 2x minus 1. Okay, so it's a pretty standard looking function. So the first thing that we want to recognize is that this argument is factored correctly. It's 2 times x minus 0. So this is an unshifted, horizontally speaking, this is a secant graph that hasn't been shifted to the right or left. However, it has been shifted down by 1 unit. So if we were to start with the basic shape of secant, we would start with some vertical asymptotes. So it's sort of universally how you want to start with functions that have vertical asymptotes, is to draw them in first so that you don't miss them. So we're going to do, I guess, 2 periods. So we know that it has this kind of up and down behavior. So I'm just going to slap that in. Guess we're only going to get a period and a half out of this. Okay, so remember with secant, the sort of normal origin is vertically halfway between this U and this peak, this valley and this hill sort of space. So it's right about on this line. So that's sort of somewhere. That's what we would maybe call the baseline, and the origin, the normal origin, is at the first local minimum. So right about here is where the normal origin would be, and recall that that's going to have the coordinate c comma d. Right now, c is 0, so that tells us immediately that this is the location of the y-axis. And the d value is -1, so the x-axis has to be up here somewhere. Okay, so how to find it though? Well, we can start with the observation that at x equal 0, secant is 1, so 2 times 1 minus 1 is 1. This point right here, this low point, is going to actually have a y value of +1. And recall that this point down here has a value of -1, or it has a y value of -1. So we can tell right away that the x-axis must fall right directly between them. Okay, so now we've got our sort of x-axis and y-axis placed. What about this point down here? Well, this is where secant is a local maximum, but this is its least negative value, right? If that's the way to think about it, which occurs when normally secant is -1. And we don't really need to worry about which argument that is, but secant does attain a value of -1. So -1 times 2 would be -2, minus 1 is -3. So this point is actually at -3. If we wanted to put some labels on the y-axis, we might call this -3, and it would make sense to call this 1, but you don't have as much symmetry there. So maybe if I put it up here as +3. Okay, so what else? What else do I need on this graph to make it complete? I need to have some sort of information about the horizontal axis. So where does it occur? Well, first, if we look at this b value, okay, note b equals 2, so the period equals the normal period, which again we noted was 2 pi, divided by b, which divided by 2, which is b, which just happens to equal pi. So what that tells us is that the distance between these successive low points, local minimum, is pi. So this must be, since we started at 0, x equals 0, this one must be pi. And if we wanted to put this one in the middle, it's going to be pi over 2. So this would, you could further figure out this first vertical asymptote occurs at pi over 4. This next one occurs at 3 pi over 4, et cetera. But this is enough information minimally to have graphed this particular function. Now notice we didn't have any vertical or horizontal translation, but you know, we would have done something very similar. We would have moved the y-axis around. Okay, so I think this video is getting a little long. I'm going to probably only have 2 segments for this because I think that the actual graphing, like taking a graph and creating an equation of secant, is not especially useful, but I will show you how to do it one time. Anyways, I'll be back with the second and probably final segment for this, for both this section and chapter. I'll see you then.